Hello everyone, welcome to this video. In this video, we'll be solving this question which states that if S be any subset of a group and H is any intersection of all subgroups of G that contains S, right? So what is H? H is the intersection of subgroups. Suppose this is S1, this is S2, this is S3 and so on, right? And all of them, they contain S, right? It is of this form. So suppose this is our S, this shaded portion is S, right? So we say what is H? H is the intersection of all subgroups of G that contains S, right? And S is any subset of a group. So within a group, right, let's define this to be our group G. Within this group we have some S subset of it, right? We are taking this, and here we have another subgroups which contain S. Let's call them by S1, S2, S3 and so on, right? And what is H? H is the intersection of all subgroups of G that contains H, right? So here we have to prove that whatever is the set which is generated by this S is equal to this subgroup H. This is the first part. So here let's proceed to prove this first part. In the first part we have to prove that this set which is generated by S is equal to H. So we will prove that the set generated by S is contained in H and H is contained in the set generated by S, right? Now because this set generated by S, this is a subgroup of G, right, which contains S. Why? Because you see it is generated by S, right, and S is a subset of this group. So, and moreover we know H is the intersection of subgroups which contain S. So definitely H would also be present here because this is generated by S, and H is that intersection which contains S. So definitely that intersection would be present within H. On the other hand, if H is a subgroup of G, right, this thing we know H is a subgroup of G and H contains S. So by definition the subgroup which is generated by S would also be present in H. So by the equation, by the inequality 1 and 2, we have H is equal to generated by S, correct? In the second part, we have to prove that if S is given to be non-empty, then the set which is generated by S, this is given by the elements of this kind where we have S1 raised to power something, S2 raised to power something and so on up to Sm raised to power m something. Now what is this m? This order could vary up to, it could either be 1 or it could be greater than 1, and all these small si's, they are taken from this given subset S of G, right, and all the powers, they are integers. This is what we have. Now taking this thing here that S is non-empty, we have to prove that S is the set generated by S is this one, right? So what we do, we name this set as V, and we will prove that V is the set generated by S, correct? So according to the definition, V is contained in the set which is generated by S, right? So let's mark this as equation 3, and moreover now we wanted to prove the set S is contained in V. So what we do, we take some element X from it, right, and we will prove that this X is also present in V, then this would be a member of this. So we take X from the set which is generated by capital S, then this small x could be written as some power of small s, right? This power is some integer, and the small s has been taken from the set capital S. Why? Because X is a member of this set which is generated by S, correct? So S is any of these elements from S, right? Because we are taking S1, S2, S3 and so on up to Sm as elements of capital S. So this small s would also be a member of capital S. Now let's take this to be S1, right, without loss of any generality. We can take it to be any other element as well. So what does it mean? We can write X as S1 raised to power k and all the other elements written as power 0. right? We can do that, there is no issue, because this is basically 1, this is also basically 1, and this is also basically 1. So this now becomes the form of our set V. It is of this kind, hence we say X now belongs to the set V, right? So that means we took some arbitrary element from here, it is a member of V. So that means the set which is generated by capital S is also contained in V. So from this inequality 3 and 4, containment 3 and 4, we have the set generated by S is equal to V, and this is what we wanted to prove in the second part. So I hope you understood this question well. Well, that is it for this video. Thank you for watching.